So now we have the examples part of our discussion on the second law of thermodynamics. In this video, we'll take a look at three examples. So first, let's have the first example. Example number 1. You have a gasoline engine in a large truck, takes in 10 joules of heat and delivers 2000 joules of mechanical work per cycle. The heat is obtained by burning gasoline with heat of combustion LC 5 times 10 to the fourth power joules per gram. What is the thermal efficiency? How much heat is discarded per cycle? If the engine goes through 25 cycles per second, what is the power output in horsepower? And finally, how much gasoline is burned per hour? So, QH, 10,000 joules of heat is taken in. So, QH is 10,000 joules and 2,000 joules of mechanical work is done. So, W is equal to 2,000 joules. For gasoline engine, for a heat engine, efficiency is W divided by QH. And we know QH as well as W, so we are able to calculate the thermal efficiency to be zero point 0.2 or 20%. For a heat engine, which in we have a cyclic process, so W is equal to Q, and Q is equal to QH plus QC. Rearranging, we have QC is equal to W minus QH. Using this equation, we are able to determine how much heat is discarded per cycle, 8,000 joules. Power, the problem is asking for what is the power output in horsepower. Power is given by the amount of work done times the cycles per second, number of cycles per second. The problem tells us it's 25 cycles per second. The work done per cycle times the number of cycles per second will give us the power in joules per second. 50,000 joules per second or 50,000 watts. Converting this to horsepower, we have 67.0241 horsepower. Finally, how much gasoline is burned per hour? At 25 cycles per second, QH is due to burning up fuel. So QH is just equal to MLC. M is equal to QH over LC. Now, the amount of mass per second that is burned is mass for one cycle times the number of cycles per second. The mass for one cycle is given by QH over LC, so we have 25 QH over LC. We know QH, we know LC, therefore dm over dt, the rate of burning per unit time is calculated to be 5 grams per second. Converting grams per second to kilograms per hour, we have 18 kilograms per hour. Next, we have example number 2. A gasoline engine has a power output of 100 kilowatts. Its thermal efficiency is 28%. How much heat is discarded by the engine in 1 minute? So output power is 180 kilowatts or 180,000 joules per second. Efficiency E is 28% or 0.28, and the time mentioned is 1 minute. T is equal to 1 minute or 60 seconds. Now, equation for power is basically work done divided by time. Therefore, we are able to calculate the total work done. W is equal to P out times T. Power times time. Efficiency of the engine is given by W over QH. Isolating QH, we have QH is equal to W divided by efficiency. Work is just power multiplied by time. Likewise, for a heat engine which involves a cyclic process, W is equal to Q, and Q is just equal to QH plus QC. Isolating QC, QC is equal to work minus QH, and QH is just equal to P out T divided by E, whereas W is equal to P out times time. So QC is now equal to P out T minus P out T over E. And we are able to calculate QC to be negative 27,771,428.57 joules. Negative because it is basically energy loss or heat loss. From QC, we are able to get the heat discarded. Heat is, QC is heat loss, so that's basically the energy or heat discarded. Getting the absolute value of QC, we get heat discarded to be 27.771 megajoules. And finally, we have the last example, example number 3. A room air conditioner has a coefficient of performance of 2.9 on a hot day, and it uses 850 watts of electrical power. How many joules of heat does it remove from the room in 1 minute? And how many joules of heat does it deliver to the hot outside air in 1 minute? So how much heat is removed from the room? So that's basically QC. Whereas how many joules of heat is delivered outside? That's basically QH. So heat removed from the room, QC, and heat delivered to the hot outside air, QH. So for this problem, we need to look for QH and QC. The problem gives us the input power. P input is 850 watts or 850 joules per second. The coefficient of performance K is 2.9, and the time given or mentioned in the problem is 1 minute or 60 seconds. Power is basically work divided by time. So work is equal to power multiplied by time. So P input multiplied by time. W is negative. There's a negative sign because sign convention for work done. Work done by the system is positive, whereas work done on the system is negative. For an air conditioner, the working substance, work is done on the working substance so that the working substance is able to take heat from heat QC from the cold reservoir. So work is being done on the system, so negative work done. Negative P input times time. We know P input as well as the time. We are able to calculate the work done to be negative 51,000 joules. The equation for the coefficient of performance is given by K is equal to absolute value of QC divided by absolute value of W. We are able to calculate QC because we know K 2.9 and we know the work done. We have just calculated it. We are able to determine QC, absolute value of QC, to be 147,900 joules. And this is the amount of heat removed from the room in 1 minute. QH is just equal to work plus QC. Absolute value of QH is equal to absolute value of W plus absolute W of QC. We are able to calculate QH 198,900 joules. And this is the total amount of heat that is delivered to the hot outside air. And with that, we are done with our discussion on the second law of thermodynamics. So that's it for now. And thank you for watching.